So kinetic molecular theory helps us to explain why chemical reactions sort of like take place at the rate that they do, sort of a molecular level discussion of actual chemical reactions. So we know that if we have a football, we throw a football and for the receiver to catch it, that there's a couple of things. We have to actually have the ball interact with the receiver. We have to make sure that the receiver is in the correct orientation, so not every time is the orientation correct. And it also has to have enough energy for the receiver to sort of like catch the ball. This sort of illustrates all of the pieces and parts, if you will, of kinetic molecular theory. So molecules must collide to react, which makes complete sense for if we're actually, all chemistry is pushing around of electrons, the molecules actually have to bang into each other. But not all collisions of reactants give products. So if the orientation isn't right, then it won't work. We also need to have a certain amount of activation energy, which is sort of like the amount of energy needed to make a reaction go. Now the easiest way, so energy of activation is sort of that minimum amount of energy to get us over the hump, which I'll explain in a second. So if we increase the temperature, the activation energy will be the same, but we have more molecules with a high enough amount of energy. So the easiest way to understand this kind of concept of activation energy is to think of or talk about what is known as transition state theory. So this is a reaction or an energy profile for a reaction. So over here on the left I have my reactants, so in this case nitrogen and oxygen, and then after the reaction takes place I have two nitrogen monoxide molecules. So for this to actually happen, these two molecules have to sort of like bang into each other, and then they have to stay together for the briefest amount of time while we sever the oxygen-oxygen bond, we sever the nitrogen-nitrogen bond, and then one nitrogen and one oxygen meet up, and one nitrogen and one oxygen meet up. So we need all four of these atoms to sort of be intimately tied to each other for a brief period of time where all those electrons are shifted. And those four atoms don't actually want to stay together, and so they are what's called a transition state, which is very unstable. And so we have to have a certain amount of energy to sort of like get over this unstable state. But then once we're over this unstable state, we can make it to sort of like the backside, which is where the products are. So one way of thinking about this is if I'm driving from San Francisco to Denver, Colorado, elevation here is sea level, elevation here is 5,000 feet, but there's a mountain pass that's 9,000 feet. If I don't have enough energy to get up over that 9,000 foot peak, I'll never make it to Denver. So if I only have enough energy to get here, then the reaction won't take place. I have to have enough kinetic energy of these two molecules. They basically have to bang into each other hard enough to make it over this hump. So what we have to understand is that as we talk about reaction rates, we talk about our rate law, and that the rate of reaction is a function of the concentration and our K value, our rate constant. So the temperature dependence is sort of buried into that rate constant. Let's think of take a step back and talk about how temperature affects reaction rate. So here's just another way of thinking about it. So here is our low temperature energy profile. So this is our measure of kinetic energy versus fraction of molecules. And remember that, when we talk about temperature, it's sort of like an average kinetic energy. And then if we have a higher temperature, that our profile will sort of like shift to the right. So there's a certain amount of kinetic energy needed for the reaction to take place. And so this is sort of like our minimum kinetic energy. So the molecules have to be moving fast enough. So at this low temperature, only this proportion of molecules down here, the low temperature, the reaction molecules down here, only these molecules have enough kinetic energy for the reaction to take place, but at the higher temperatures this curve sort of shifts to the right. Obviously we have more molecules that have that minimum amount of kinetic energy to make it over the hump. Now we can quantify this relationship between temperature and rate going up, because again our rate constant, our rate equation does not have a temperature function in it. So here is what is known as the Arrhenius equation, which actually relates our rate constant for a particular reaction, and there is our temperature dependence. E sub A again is our energy of activation, And then A is what is called a frequency factor. Now, if you recall, we talked about how rate of reaction is a function of four things: temperature, concentration, surface area, and presence of a catalyst. And when temperature and there's our dependence there, so it's buried into the K. Our concentration is explicitly in our rate law. This A is the closest thing that we can get to that's related to that surface area issue. We call it a frequency factor, which is sort of a function of the collision frequency, which is again almost impossible to measure. So we just sort of, like, whenever we do these reactions, we just assume everything is as well mixed as possible, so it sort of like comes out in the wash, so to speak. So we'll never actually explicitly calculate A. So this equation isn't very useful in and of itself at one particular temperature, but if we combine the K at one particular temperature and the K at some other temperature, well, E sub A is a constant, R is a constant, and A is a constant, and the A constant will actually cancel out, and so we get this more useful version of the Arrhenius equation, which relates to reaction rates, to the energy of activation, and the various temperatures at K. So K1 represents the rate constant of the reaction at T1. This is the most effective way for us to be able to calculate the energy of activation at any particular temperature. We simply set up an experiment where we run the reaction at one temperature, determine the rate constant, so the reaction at some different temperature, determine the rate constant of that reaction, and allows us to calculate E sub A. Just want to note that we don't explicitly have to know the value of K2 or the value of K1, we just need to know their ratio. So if we're actually doing this in terms of experimentally, we just need to know what the ratio of the rate constants are. And that's good enough. Good luck.